This video is going to look at the acid-base equilibria topic, and in particular we're going to focus on buffers and buffer calculations. So if you've not covered the sort of more simple, straightforward weak acid calculations using the Ka equation, I would make sure that you go over that topic before you watch this video, otherwise it's not going to make a lot of sense. But buffers is often the more difficult part of this topic and the more difficult part of the calculations, which is why we're focusing on it in this video. So first of all, we need to know what a buffer actually is, or more correctly, what is a buffer solution? Now that question could be quite wide because we could be asking what a buffer does, which is usually what the question's asking. So if the question is asking what a buffer does, then we're going to say that it resists changes in pH when small amounts of acid or alkali are added. That makes them super important for pretty much anything biological, because you've got enzymes and things, anything in a living system is super sensitive to changes in pH. So everything in your body is in a buffer solution, basically to resist changes in pH. The small amounts is really important, and we will be coming back to that lots of times when we look at the explanation later on. So the other thing about deciding what a buffer is what does it actually contain? What physically is it in terms of chemicals? So it comes up when we study weak acids. In this video, I am going to be representing weak acids, the undissociated acids. So when you put a weak acid such as ethanoic acid in water, we know that weak acids only partly dissociate into H+ and the negative ion. And so in our calculations, just to make it easier to represent that, that is going to be our undissociated acid, which normally for a weak acid with a Ka value, typically around 10 to the minus 5, that is most of the acid is undissociated. And then if I look at the other side of the equation, obviously I've got H+, which is what pH depends on. And then I've got A-. Now there are different ways that we can describe this. We can call it the salt of the acid. We can call it the anion because it's just simply the negative ion. So for example, ethanoate. And we can also refer to it as the conjugate base. So all of those are kind of accurate. You might be thinking it's technically not the salt, but later on it will be. We can make more of it by adding the salt. So that is the thing about a buffer. A buffer suggests that it's to respond to changes. We're thinking about Le Chatelier's principle. Le Chatelier's principle requires obviously a reaction at equilibrium, but you can't respond to changes in either direction unless you've got enough of both sides. So this is really important. A buffer needs to contain not just the acid, because if I just put the HA into solution, it's not going to dissociate much. So it needs to contain reasonable amounts of the weak acid, so ethanoic acid, propanoic acid, and its conjugate base or its salt, so sodium ethanoate, potassium propanoate, etc. We will come back to how it works right at the end of this video, and that's because it's much easier to explain once we've done lots of calculations how the buffer is actually responding and resisting changes in pH. It's not magic, it's not stopping the changes. Both of those things, though, need to be present in large quantities. When we say large quantities in chemistry, we don't actually mean large quantities. We mean if one of them is 0.1 moles per dm cubed, the other one has to be of a similar concentration. So it cannot be 0.00001. It won't work. Okay, so imagine that HA and A- are similar sizes in quantity. When we do the calculations, we are going to concentrate a lot on using this Ka equation. When you have a weak acid on its own, you will have been using this Ka equation and you will have been simplifying it to H plus squared at the top. And that's because if you have a weak acid on its own, we make this approximation that the H plus in solution only comes from dissociation of the acid, and therefore we haven't added any salt, so we haven't added any of that A minus, so they're equal. That is not the case, so we do need to be really careful with our calculations that H plus does not equal A minus because I have added extra A minus. I have created more A minus in my solution. And in fact, there are lots of ways we can make a buffer. We're going to look at 3 different ways that you could take a weak acid and make a buffer solution from it, because they all involve calculations, luckily. When we do the calculations, so we can write it out like that, and we know that the square brackets equals concentration. However, for the purposes of these calculations, it is, oh, I forgot about this bit, yeah, so the pH of the buffer depends on the ratio between the salt and the undissociated acid. That's actually really important, and in fact is related to how we're going to write the equation. We're going to write the Ka equation like this instead. So this part here is what I'm calling the ratio between the salt and the undissociated acid. So why is that important? So H plus does not equal A minus. A minus has got its own value. Okay. pH depends, obviously, on the H plus concentration. That has to be in concentration units, so it has to be moles per dm cubed. When we put it into the equation for pH, our minus log of H plus concentration. Ka is obviously constant. We're not going to do any calculations where we change the temperature or anything, and if we do, we'll be given a different Ka value, so it's not a problem. So hopefully you can see that basically, because Ka is constant, H plus depends on this number, which is a ratio between 2 things. And basically, because it's a ratio of A minus over HA, we could have it in moles per dm cubed, so concentration units, but we could have these numbers in moles, because moles divided by moles has no unit, and concentration over concentration has no unit. And whatever moles I've got of HA and A minus, they're in the same volume, okay, because the buffer solution is a single solution. So therefore I could sort of change them to concentration, but there's no need. And hopefully as we go through the calculations, you'll realize why it's a lot easier to think of it as moles of salt divided by moles of acid. Okay, let's have a look at some calculations then. And the first 3 example calculations we're going to look at are ways that we can make a buffer solution. So one way that we can make a buffer is to simply take a solution of weak acid and to mix it with a solution of its weak salt. So that's what we've got in this question. It says calculate the pH of a buffer made by mixing 50 centimetre cubed of 0.1 mole per dm cubed ethanoic acid and a different volume, 35 centimetre cubed, and a different concentration, 0.2, of sodium ethanoate. So the first skill to get into as you're just working out how to do buffer calculations is just to identify that these numbers here, ethanoic acid relates to HA in my equation, and these numbers here say sodium ethanoate. As soon as I see sodium or potassium or in group 1, then I know that that is my salt, which is my A minus in the equation. Sodium itself is not going to appear in any of these calculations. It's completely a spectator ion that has no effect on pH, so don't get confused about sodium and start putting Na plus anywhere in your calculations. So we know that Ka equals H plus times A minus over HA. You're going to be very bored of this equation by the end of this video, but that's a good thing because we want to be bored by it, because then it's hopefully easy. So what we're going to do, we're going to work out moles. We're going to work out moles of HA That's easy enough. We have a volume and we have a concentration. So we've got 50 centimetre cubed. Divide that by 1000 gives me 0.05, times it by the concentration 0.1, and I get 5 times 10 to the minus 3. I got my moles of A minus. That's going to be 35 divided by 1000, so 0.035 times by 0.2, that gives me 7 times 10 to the minus 3. So when you mix these solutions, the number of moles does not really change. Okay, so I've got my separate solutions. They're in a bigger volume now, so they have not got the same concentrations. That's why I can't put simply 0.1 and 0.2 into this equation, because they do not have those concentrations anymore, because I've not mixed equal volumes. So they've been diluted, their concentration has changed, but that's okay, because I can put moles into this ratio. What's even nicer about it being a ratio is if you look at what this number now equals. I'm going to insert the value for A minus, 7 times 10 to the minus 3. The value for HA is 5 times 10 to the minus 3, so biggest issue in this equation is doing it the wrong way round. It's really nice because I can just cancel out that 10 to the minus 3, and that makes my calculation so much nicer. It's basically 7/5. So rearranging H plus, and if you're bad at rearranging, it happens, especially when you're a bit stressed, then I recommend you actually just do 7 divided by 5 first, and then sort of input that where the A minus HA number is, and then move it across. I'm going to just leave it as it is. It's Ka, and then because it's times 7 and divided by 5 on the right hand side, but I'm moving it to the other side because I'm taking this over here and getting H plus on its own, then I am going to times by 5 and divide by 7. That gives me an H plus concentration of 1.7. No, it doesn't. Sorry, I was just reading my calculation bit. 1.214 times 10 to the minus 5. Minus log of that gets me the pH, which is 4.92. All done. Okay, so that is mixing two solutions. We find moles of A minus, we find moles of HA, and we insert it into that equation. Here is a different way of making a buffer. So you could take a acid solution, a weak acid, in this case ethanoic acid again, and you could add solid sodium salt of your acid to your solution, because all the sodium salts are the weak acids. Because they're sodium salts, they're going to be ionic, they're going to be soluble in water because they're sodium salts, and they'll be solid, so they'll be easy to handle. So we're going to do a really similar method, except this question is taking it from a different direction, because instead of being asked to calculate the pH, we are being given the pH and asked to calculate the mass of the sodium salt that we would need. So let's work it through. We are still going to use this equation. Ka is concentration of H plus times moles of my salt divided by moles of HA. Now let's look at what we have. We've got Ka, and because we have pH, we can calculate H plus. So if pH is minus log H plus, then H plus concentration is 10 to the minus pH. So that is 10 to the power minus 5.4, which is equal to 3.98 times 10 to the minus 6. So I've got a value there. And let's now calculate my moles of HA. So I have a volume and a concentration. I have a 500 centimetre cubed of buffer solution, or what's going to be my buffer solution. So that is 0.5 decimetre cubed times by 0.1 gives me 0.05. So 0.05 is moles of HA, I've got my H plus, I've got my Ka. So I can now rearrange to find moles of that negative ion, that ethanoate ion that I need to be in this solution. So it's going to be Ka times moles of Ha divided by concentration of H plus. So just really focusing here, I am not just being lazy and leaving out some of my square brackets. Remember that when I use pH calculations, H plus is always in concentration units, it's always in moles per dm cubed. But what I've just calculated for Ha was not. I did moles. You can do this calculation using concentration, it's just then that you will calculate concentration of A minus, and then you'll have to sort of go backwards and work out the moles. I recommend moles, 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 just every calculation that's hard. Make everything that you can into moles because it's just easier. So moles of A minus is that. I'm going to put all my numbers in, but I'm not going to write them all down because I'll run out of space. So moles of A minus is 0.214. We could take a moment and just think, does that seem a sensible amount? Yeah. We don't want a moles that is like 10 to the minus 5 or 10 to the minus 6 or even like thousands of moles, do we? That seems like a reasonable number of moles of something. From there, we then are working out mass. So now we're just back to mass equals our moles times mR. I've got my moles of A minus, but it's going to be, and A minus is the ethanoate ion. And so I need to work out my mass of sodium ethanoate. So hopefully we should be able to just sort of draw out the formula of a weak acid. So this is the acid, not the salt. This is ethanoic acid. To make ethanoic acid into sodium ethanoate, I just take off the H plus and replace it with an Na. So now I've got a formula because I need my formula to calculate my Mr. Add it all up, trust me, Mr is 82. And so the mass of sodium ethanoate that I need to add is 0.214 times 82, and that gives me 17.6 grams to 3 sig figs, which is what I'm going to leave most of my calculations to. Again, it's quite a large amount, but it's quite a large volume of solution, 500 centimetre cubed, so that's fair enough. It's not a ridiculously large amount, okay? If I was trying to add 176 grams to 500 centimetre cubed, I would think I'd done something wrong, right? Because it's very difficult to dissolve that much into that much solution. So far, making buffer solutions, we've considered having two separate solutions, one of the salt and one of the acid, and just mixing them. In this example, we've taken the weak acid solution and added the solid salt. So what could possibly be the third way to make a buffer? Well, what we can do is we can take a weak acid, in this case propanoic acid, and we can add a little bit of alkali. We're not completely neutralizing it. If you completely neutralize it, you will have no HA and all A minus, and that's not a buffer because we need sort of both to be present. But if you take HA and you add some sodium hydroxide, again, remember sodium, unless we're working out the mass of something, I don't really want sodium in my equation. So it's the hydroxide bit that's reacting. Sodium hydroxide is a strong base. This is not an equilibrium reaction. It is going to make water and my salt. So by mixing sodium hydroxide and propanoic acid, if you really want the non-ionic equation, here it is. It's going to be H2O plus NaA. That's not very helpful. It's going to make sodium propanoate in solution. And because I'm only adding some moles of sodium hydroxide and I'm not adding enough to completely get rid of HA, then what I'll end up with is a solution that contains both. So it will contain some moles of the weak acid that's still left, and some moles of the salt. And this is really important, not because it's particularly how I might make a buffer, but because it happens in the middle of a titration. So the pH curve bit where we're going up like that, this part here where I haven't yet neutralized it, so I've not yet got to my equivalence point, and it's sort of in the middle of my titration before I get to the end point, that is where my acid is actually going to start behaving like a buffer solution, because it's got both HA and A- present in like reasonable amounts. So how do we do the calculation? Moles, moles, moles. Remember, it's all about moles. So this time, however, my moles doesn't stay the same all the way through. So when we mixed HA and A-, they don't change the concentrations or the number of moles of each other. But when I mix HA and sodium hydroxide, then what is going to happen is that my moles of HA, undissociated acid, is obviously going to go down because I'm reacting with alkali. And my A-, which started at 0, or my salt, is going to be made. So what I need to work out is how many moles of weak acid I have left and how many moles of salt I made. Those gives me my values for my A- and HA to go in the good old Ka equation. So we need to have initially, before mixing, it's quite similar to an ICE table, but not exactly the same. So initially, I have 25 centimetre cubed of 0.2 mole per dm cubed propanoic acid. So HA, my moles is 0.025 times by 0.2, which is 5 times 10 to the minus 3 moles. Then I'm going to look at, I've added OH minus. Let's work out how many moles of OH minus I've added. It's going to be 30 over 1,000 times 0.1, which is 3 times 10 to the minus 3. So it's very important in this calculation that that number is less than my HA. Otherwise, this is not going to work. If I add more sodium hydroxide, it's just not going to work because I'll have completely got rid of HA and it won't be a buffer anymore. All right, so all I have to work out now is the finally, in my final mixture, my moles of HA is going to be 5 times 10 to the minus 3, take away 3 times 10 to the minus 3. It's always going to be a 1-to-1 ratio. Weak acids always just have that, they're always monoprotic in this context for these types of calculations. So my HA that's left is now going to be 2 times 10 to the minus 3. 5 take away 3. Meanwhile, I have made a load of A-. So we're going to assume that however many moles of A- I had at the start, was basically 0 compared to what I'm adding. Okay, we're doing that all the way through. So the new moles of A- is simply whatever was made by adding the sodium hydroxide. Just like in the previous equations, we assumed that, again, like the mass of sodium ethanoate, it was just all the moles of A-, and that there wasn't really any moles of A- in the solution to start with, which is an accurate assumption because it dissociates so little that there's hardly anything in there. So all of my sodium hydroxide is going to react with HA to make A-. So I've got 3 times 10 to the minus 3 moles there. Beautiful, we can get rid of that 10 to the minus 3, forget about it. Ka equals H plus times A- at the top, 3, HA at the bottom, 2. I mean, you can put the 10 to the minus 3 in if you want. It's a lot of things to type on your calculator and it's not necessary because they cancel out because they're top and bottom. So H plus is going to equal Ka times by 2 over 3. Just rearranging it, bringing it to the other side. If we put in the value for Ka that we've got, times it by 2, divide it by 3, I get a value for H plus of 8.67 times 10 to the minus 6, and I put it in my calculator, do minus log equals, and that is 5.06. So those are my 3 different ways of making buffer solutions. Mixing 2 solutions, adding a solid to a weak acid, or in this case, adding an alkali to a weak acid and neutralizing or creating salt out of some of the acid. So what we haven't done anywhere in this video yet is actually looked at what happens when I add an acid or a base to my buffer solution and how it resists changes in pH and how we calculate the new pH when a small amount of acid or alkali is added once I've made this buffer solution. So here is an example that we're going to work with. So we, again, starting the new buffer solution, I'm doing a new one every time just so that we can really get used to doing this calculation, and hopefully you've really got used to using that Ka equation by now as well. So we have the buffer solution already, so we're given the concentrations of propanoic acid and sodium propanoate, and this time we have to calculate the pH after adding, this time, small amount, so 5 centimeter cubed of 1 mole per dm cubed HCl, and we also have a volume of the whole buffer solution. So that 200 centimeter cubed contains already the propanoic acid HA and sodium propanoate A minus. Then we add acid to it. Hopefully we've got into this idea of using this equation and realizing that we must have A minus and HA in moles, because if I add a particular number of particles of acid, moles of acid, you can't take concentration per concentration. It doesn't make any sense because the volume determines how many particles there are. So when I add acid, acid will react. So if I have HA present, I have H plus and I have A minus. By adding acid, I am adding H plus. The equilibrium will shift to the left. But what does that mean in terms of moles and doing the calculation? Well, what it means is that H plus that I add will react with the A minus. So that means that my A minus, the number of moles of A minus, and therefore the concentration, will go down. Makes sense, right? And then if I am adding acid, it will react. They will join together to make HA. So it means that my HA goes up. So in the previous example, when I was making the buffer, I added alkali, and of course what that did is shift the equilibrium to the right. So I made more A minus and I got rid of HA. The difference here is that I had amounts of HA and A minus to start with. So previously I had no A minus in the buffer and I was just calculating the change in HA. Here they are both going to have an initial number of moles, both HA and A minus, and I'm going to calculate how they change. So let's calculate first. Initially, my moles of HA. So hopefully we're getting into the swing of our mole calculations now. It's 200 centimeter cubed, so that's 0.2 decimeter cubed times 0.1 is my concentration for propanoic acid, gives me 0.02. And then my moles of A minus, whoops, I don't know where my minus went, like that, is going to be the same volume, 0.2, different concentration, 0.2, so 0.04. So that's what I've got before I add my acid. So this is what I mean by it being a little bit like an ice table, so the change. So my acid, I have 5 centimeter cubed of 1 mole per dm cubed, exactly the same thing, going to calculate moles again. So 5 divided by 1,000 times by 1 is going to give me 0.005, or 5 times 10 to the minus 3. I'm writing it as 0.05 because it's just a little bit easier to visualize with the numbers that we've got. how these two are going to change. Of course, use a calculator if you can't see what's going to happen, because we'll just use a calculator anyway so you don't go wrong. So the change that's going to happen because I added the H+, and again we're assuming this is a complete shift and we're not worrying about the small amounts that the equilibrium might shift back and forwards. The HA is going to increase, so it's going to go up by 0.005 because we're shifting left, whereas the A- is going to decrease, it's going to go down by 0.005. It's always going to be the same amount that one goes up and the other one goes down. So the new moles of HA is going to be 0.025, and the new moles of A- is going to be 0.035. Now I've got values that I can put into my Ka equation. Let's just rearrange it just because I'm going to run out of space. So H+ is Ka times HA over A-. These are all in moles. Ka 1.3 times 10 to the minus 5. Oops. Times by 0.025 divided by 0.035. Answer for H+ concentration is 9.286 times 10 to the minus 6, and I've just got enough room to do the minus log of that value to find the pH, which is 5.03. So that is the new pH of the buffer. Now, because we've been given the original concentrations, 0.1 and 0.2, and we've got that Ka equation there, it's actually super easy just to tap into your calculator and work out what the pH would have been before, because we just put in 0.2 and 0.1 where A- and HA are, and we can then calculate what the H+ and therefore the pH. So the pH of the solution before I added that acid was a 5.19, and now it's 5.03. You might be thinking that 5 centimetre cubed of 1 molar acid is not very much. If I added that to like the same volume of water, it would probably have a pH of less than 2. So you're talking about a tiny change in pH compared to what would happen if the salt and its weak acid were not present to buffer that. Last example would be adding alkali to a buffer solution, and most of it is really similar. We're still going to use the Ka, so we're going to find our initial moles of HA and of A-. So straight in we can do that. Let's have a look. We've got the concentration of HA and A-, and then we've got the volume. This is 500 centimetre cubed, so 0.5 decimeter cubed. So for moles of HA, 0.25 times 0.5, which is 0.125, and then A- is 0.15 times the same volume, which is 0.075. Okay, now we're adding alkali, colour coding. We're adding that many moles, so we don't need to calculate moles. It totally depends on the number of marks available in the question, but they usually don't actually make you calculate moles 3 times in a row, simply because if you get it wrong 3 times in a row, it penalises you a lot. So often they'll give you like moles and the volume and concentration of a couple of things and the moles of something else. So 0.02 is what we're adding. We're adding alkali this time to this equilibrium. Whoops, this equilibrium. Adding alkali will shift the equilibrium to the right-hand side, because there's 2 ways to look at it. Either you can look at the alkali will reduce the H+ concentration, and if you remove something on the right, equilibrium will shift to the right to bring it back that concentration. Or you can simply look at it as the sodium hydroxide reacts directly with HA to make A-. Either way, the upshot is, doesn't matter how you visualize it, because it's all just happening at the same time, is that HA will go down because I'm adding alkali, and the salt will go up because I'm making more salt. The change, therefore, for HA will be minus 0.02 this time, and for A minus will be adding 0.02. So the new moles, the final moles in the solution for HA will be 0.105, and for A minus will be 0.095. We're going to pop that all into the equation, so I'm going to go straight into rearranging. H plus is Ka times HA over A minus. So 1.5 times 10 to the minus 5 is different acid every time, just to give you a bit of variety in your Ka values. And then that is going to be times 0.105 over 0.095, gives me H plus concentration of 1.658, 10 to the minus 5, do a minus log, and my pH is 4.78. Again, it's relatively straightforward for me to compare this with what the solution was before I added the alkali, and it was 4.6. So again, less than 0.2 of a pH change from adding quite a significant quantity of sodium hydroxide. That would be enough to make the same volume of water go to at least pH 10, 11 from 7. So huge jump in pH. Whereas this has only gone up a tiny amount. So that just leaves us with our very last thing to explain with buffers, which is actually properly explaining why they are able to do what they do. So we could use Le Chatelier's principle. We could look at the fact that, of course, we have an equilibrium. If we add acid, the equilibrium shifts to the left to remove some of the excess H+. And if we add alkali, the equilibrium will shift to the right to make more H+. It's okay. It's not very mathematically rigorous. And if we actually think about this equation as we've been writing it the whole way through, what we've been saying is that pH depends on this ratio, moles of A minus to HA. And when we've just been doing our calculations, for example, in the previous one where we added alkali, which is the most common type of question, we said that adding alkali increased this and decreased this. So it's changing that number. And we said that pH depends on that number because H+, basically, if Ka is constant, depends on that ratio. So we are changing that ratio. And in fact, we did just see, of course, that the pH did change. So what's important here is how significant it is, how much we're changing it. And that's why we go back to the buffer needs a large amount of both A minus and HA present, otherwise it doesn't work. Otherwise anything could act, otherwise just like a solution of sodium methanoate could act as a buffer, or the acid on its own. So what we want to be able to say is that, let's use the alkali example. If we add OH minus, then we can say that the position of equilibrium shifts to the right hand side, and that's because we're removing H+, and therefore the equilibrium is responding. And we're making, so we can say that the concentration of HA goes down and the concentration of A minus goes up. But because the weak acid and the salt are present in relatively large amounts, which is sometimes called a reservoir, then we can say that the ratio remains relatively constant. So as soon as you get to a point where your HA is almost used up, which you get in your titration curve, it stops really being a very good buffer. So this only works if you have, I'll just correct my spelling, only works if you've got relatively large amounts or a large reservoir of both the weak acid and the salt present in solution. And that's how a buffer works. It also explains brilliantly how buffers also resist changes in pH if you just simply change the amount of water. So if you dilute a buffer solution, it will maintain its pH for quite some time, because even though you're diluting it, you are diluting A- and HA by the same amount. That's really important in blood if you think about the differences in your blood volume over the day, whether you're dehydrated or hydrated. You can't have your pH just randomly changing just because you are feeling a bit dehydrated. So that's also another important point about buffers.